In quantum mechanics, the outcome of a measurement is random, and the measurement changes the state. In this video, I will show you the mathematics of these measurements. You will learn how to formulate a measurement with bra-ket notation. In ket notation, measurements are written down with operators, and operators are matrices, and they work on state vectors. As a preview, the measurement operators for the z-basis are m0 is 0, 0, corresponding to the 0 measurement outcome, and m1 is 1, 1, corresponding to the 1 outcome. Now you will quite often see this kind of notation, and I was quite confused about this when I first learned about quantum mechanics. But it really just means a multiplication of a ket with a bra, but then written down in a lazy way. So for example, if we take 0, 0, then that's nothing else than just ket 0, bra 0. So just a multiplication of the column vector 1, 0 and the row vector 1, 0, which results in a 2 by 2 matrix 1, 0, 0, 0. Likewise, the measurement operator 1, 1 is the matrix 0, 0, 0, 1. There are three different rules you need to obey in order to write down a measurement in ket notation: the sandwich rule, the identity rule, and the normalization rule. Let's start with the sandwich rule. Suppose we have our familiar state psi is alpha 0 plus beta 1, and we want to know the probability of a certain measurement outcome. Now, calculating the probability is the same as calculating the expectation value of the measurement operator. We calculate the expectation value of an operator by sandwiching it in between the state vector. So P is bra psi, M ket psi. So for instance, if we want to know the probability of measuring 0, we have to calculate the expectation value of M0. So if we work that out and fill in 0, 0 for the measurement operator, this is the same as the absolute value of bra 0 ket psi squared, which is the inner product of the 0 state and the psi state. We can fill in the state vector psi here. So bra 0, alpha ket 0 plus beta ket 1. And then take the absolute value squared of that. Now I want to add a little side note here, that the inner product of 0 with itself is 1, and the inner product between 0 and 1 is 0, because the states are orthogonal. Therefore, we can just cross out the beta term, and we're left with the absolute value of alpha squared. The identity rule tells that the sum over all measurement operators in a basis should be the identity matrix. And remember that the identity matrix is the diagonal matrix 1, 0, 1, 0. Let's check this for the z-basis operators. m0 plus m1 is 0, 0 plus 1, 1. And if we fill in the matrices 1, 0, 0, 0 and 0, 0, 0, 1, we can see that we indeed end up with the identity matrix. Now, why is this the case? Because of the Born rule. The probability of all measurement outcomes should add up to 1. Now, if we use the sandwich rule to calculate the total probability, we do the following operation. So P total is P0 plus P1, which is the sandwich of M0 plus the sandwich of M1. Now we can group M0 and M1 together inside the sandwich. And noticing that this total probability should be 1, we can see that M0 plus M1 should be the identity matrix. The last rule to keep in mind is the normalization rule, which is about the state that remains after the measurement. So suppose we have a state psi and we measure the state in a z-basis. The measurement outcome is 0 and the remaining state is phi. Now we could ignorantly say that phi will just be the multiplication of the measurement operator m0 and ket psi. Let's work this out. 0, 0 times alpha 0 plus beta 1 Now we can cross out the beta term again, and we're just left with alpha ket 0. Now there's something wrong with this, because in general the norm of alpha is not 1. Therefore, the state phi is not properly normalized. Instead, we should normalize phi with 1 over the square root of the probability. And if we work this out, we will get 1 over the square root of the absolute value of alpha squared times the measurement operator 0, 0 times the state psi, which results in alpha over the absolute value of alpha times ket 0. Now the length of this vector is 1, and this prefactor will just lead to a global phase vector, which is unobservable, and we could therefore also leave it out. So with these three postulates, we are able to make a projective measurement in ket notation. Now we assume that the measurement was in the z basis. So if we would switch to the x basis, for instance, the measurement operators would become m plus is plus plus, and m minus is minus minus. And similarly, for the y basis, they would be I and minus I minus I. And you can check for yourself that the identity rule is satisfied. These measurement operators describe projective measurements, and sometimes we also call them projectors.